I apologize for my Italian. Thank you, Mario, for a very kind introduction. It is an honor to be here with you today on this very special occasion. First of all, I would like to congratulate the new PhD doctoral graduates. So can we give an applause to all of you? It's an honor to be here on this very special day for you. And as you launch your careers in education, research, industry, or whatever awaits you. Also, I understand there are parents and families here. I hear some of the younger children during the introductions. So, congratulations to the families and the parents. As a parent, I know how wonderful it is to see your children graduate with this level of accomplishment. So, here is an applause for the parents. Finally, I'd like to congratulate the professors. Congratulations to you for producing these graduates. And as a professor myself, sometimes it's nice to see them go. So we wish everybody here well, and I look forward to sharing with some of the new graduates some of my own experiences. What I hope to do today in the next 30 minutes or so is to share with you, the new graduates, some insights that I may have gained in my pathway in research. Now, there will be many differences, of course. Nobody's path is the same, but some of the lessons maybe are very useful. And the lesson that I would like to emphasize the most is in the title here, patience and urgency. Patience, keep your eye on a long-term goal, and I'll illustrate how I did. And it may take many years to accomplish. It may be slow go at first, especially in a difficult economic time. But keep your eye on what is truly important, not what is less important. And urgency. Don't, we all have to be aggressive. We have to push the boundaries, especially when we're young. And these are contradictory to each other, to be patient and yet to be urgent. If you can find the right balance between those two, my belief is that it will be good for you and for the society that you contribute to. Now, I think I'll begin this story with last October in 2013. I received a certain phone call from Sweden. Now, one of the first things that you were asked as a new Nobel Prize laureate is, how did you learn that you were to receive the Nobel Prize? And some of you may know this is an absolute secret. You have absolutely no idea that it will happen. And this is a picture of the secretary of the Medicine Nobel Prize Committee in Stockholm, at Karolinska Institute. He knows the answer. He knows, I hope this is a pointer, no? We had audio-visual difficulties already. How do you say slideshow in Italian? How do I get this back? There it is, the universal symbol of slideshow. I think we'll skip the pointer. Okay, this is Professor Hansson. Now, Professor Hansson has the nice duty to place a telephone call at about 10:30 in the morning at the beginning of October. So Professor Hansson knows exactly who will win this year's Nobel Prize in medicine. The recipient, however, does not yet know. The recipient is actually in bed in New York with his wife, sitting here with me today, Professor Joy Hirsch, and is waiting not at all. In fact, the professor is completely asleep and receives a phone call at 4:30 a.m. and tries very hard to wake up. The first news interview is exactly... So this is what actually it was like to receive a Nobel Prize. You get woken up in your bed, and 5 minutes later, the journalists are on the phone asking, what do you think about this, and what do you think about that? And actually, quite frankly, you have no idea what to think, except you want a cup of coffee and a shower. Now, the story of my research and the story of this Nobel Prize actually begins many years earlier. And I showed this slide. This is a picture of Professor George Palade, who received the Nobel Prize in Medicine 40 years, almost exactly, 40 years before me. And he was the founder of the field that I studied, which is called cell biology. Also, he was a professor at Yale University. Also, he founded the first department of cell biology. Also, I am the chairman now, today, the director of this department. And actually, I sit in Professor Palade's office. So it's a funny story of history coming full circle, because I took up some of the challenges that Professor Palade provided to the field during his years of discovery. And in a way, this is sort of an appropriate theme for today, because the new graduates today, you create your own path forward. But you build on what you've been taught by your professors. And you will teach the new students in the future how to go about making discoveries in their own time. Now, what Palade discovered and what he received the Nobel Prize for was for the discovery that the organization within the cell is very complex. There are many proteins within the cell, and Professor Palade and others discovered that these machinery, the machinery that operates the cell, called proteins, that this machinery is highly organized and orchestrated within the cell. We discovered there are special compartments within the cell. Here we are right here. Here is a compartment called the Golgi apparatus. It was actually discovered by Professor Golgi in Padua, one of the first Nobel laureates in medicine, in the early part of the 20th century. And what Palade discovered is that these proteins are directed first from the chromosomes inside the nucleus to be manufactured in the cell, and then distributed within the cell by a process called intracellular protein transport. The cell is like a complex city. It has perhaps 20 different locations. There's perhaps Verona over here, and there's Roma over there, and Milano over there. And each of these newly made parts has to be distributed. Some go to Roma, some go to Milano, some go to Verona. Probably the best ones go to Verona. And there has to be a delivery system. Professor Palade discovered the nature of this delivery system. Imagine that there are trucks within the cell, kind of Federal Express trucks. The cargo gets loaded in the Federal Express truck in Roma, and it delivers the cargo, the best cargo, to Verona. There has to be a way within the cell on a microscopic level for these trucks to recognize their cargo. They need to travel within the cell and to find the right place to deliver. And just as a cell is very complex, in Italy you have many cities. I understand the traffic patterns are not always perfect, but the cell is perfect. And what I set out to discover was how this delivery system works, how the delivery system can work at a molecular level to take the correct cargo to the correct places within the cell. And this happens within each of the cells in our body constantly. At any one moment in time, there are 100,000 different types of cargo being made within our cells. And at any one time, there are the delivery trucks, which we call vesicles, transport vesicles. This is a picture of one, a diagram of a transport vesicle. The transport vesicle leaves, for example, Roma, and travels over and delivers its cargo, for example, to Verona. And there are perhaps 10,000 of these containers in the cell at any one time. Each one lives for only a minute. It forms, it takes its cargo, and it delivers it. This is an amazing thing. And what we set out to understand was, how does this work at a genetic and a molecular level? Now, why is this important, and why is it important to physiology? Why is it important to medicine? It's important because so many processes in our body depend on what we call vesicle fusion, which is the delivery process itself, in which the cargo is delivered to the correct place. This includes the division of the cell itself. When a cell grows and divides, it has to double and make two cells. Each cell will have a perfect copy of each of the places. So if a cell has one Roma, one Verona, one Milano, each of the next cells of the next generation needs also to have its own city. So the cell has to have a way of making perfect copies of its own organization. This process relies on vesicle fusion and delivery in a way that I will describe. And when this process is imbalanced, we have imbalances in the growth and the division of the cell, which can include the development of cancers. Cells also need to communicate with each other. And among the categories of cargo that are delivered are cargoes that are actually delivered to the outside of the cell. Hormones in the blood. We've all heard of insulin, for example. Insulin is produced in the pancreas. It is released by a process of vesicle fusion. This, in the microscope, is a picture of a vesicle, a very large granule, containing insulin, which in a moment will release the insulin to the blood by membrane fusion. And the balance of the release of hormones and the sensing of hormones is mediated also by the very molecular process that I'll describe. And of course, imbalances in these processes lead to diabetes and obesity. So there's considerable medical interest and importance in this process. And finally, not least, we have the area that Professor Buffelli works in, which is neurophysiology. Our brain itself depends on membrane fusion. Inside each nerve cell, there are many little vesicles, such as are shown here. Tiny little vesicles. Each vesicle contains neurotransmitters. Probably everybody here has heard of neurotransmitters. They cast signals between the cells in the brain, the neurons. And when we have imbalances in neurotransmitters, such as serotonin, our mood is affected, and our ability to communicate, to think, and to function is affected. So understanding how these neurotransmitters are controlled and released is very important for understanding the basic function of the nervous system, but also neurodegenerative disorders and psychiatric disorders. And what I will tell you today is that all of this depends on one very fundamental pathway, which is the pathway of membrane fusion. And it is that discovery that was really recognized, that was made by myself and my colleagues with whom I shared this Nobel Prize in Stockholm last October. So I'd like to tell you very briefly, and mostly in non-scientific terms, or non-technical terms, that discovery. You always have to have an idea to make a discovery. And if you have, most of the time, our ideas in science are wrong. We start out with, this fellow may have a very good idea, we just can't figure out what the idea is quite yet, but in a couple of years, you never know. I think my grandchild is about the same age, so we're used to this. Most scientists, you have to understand, start out with the wrong idea. we mostly fail. We succeed perhaps 1% of the time. If we're successful 1% of the time, that's really very good. A scientist who's less successful perhaps succeeds only 0.1% of the time. So you must always tolerate the ability to make adjustments to your idea. But usually the simplest idea is the correct idea. If you're studying something fundamental, it's usually the simplest idea. Now, the process of membrane fusion before my entry into the field, frankly, was thought of in very complex ways. And the idea was that the reason you could deliver from Milan, for example, to Verona, or Verona to Milan, is because these two destinations were very close in each other in the cell. And so as a result of their physical proximity, transport vesicles, or the carriers, or the trucks, could go from one location to the other very easily because the two cities were next to each other in the cell. My idea was a little different. My idea was, actually, the truck has all the information, just like a Federal Express truck or a delivery truck. When the driver gets into the truck, the driver knows where he is going to go. So he's on his own. He can go anywhere he wants, but he knows where he's going to go. That was actually a radical idea. And in chemical terms, for those of you who are new graduates and know some biochemistry, the idea was that each vesicle carries intrinsic chemical specificity and knows exactly where it will go because it has a molecule that marks its surface that will meet a receptor and will enable vesicle fusion and the delivery process to occur. Now, the implication of this idea is important because it means that the process of delivery by vesicles must be mediated by a biochemical process that is intrinsic. And this means, in turn, that it can be reproduced in a cell-free extract. And what this also means is that the process, because it can be reproduced in a test tube, can be studied by the tools of chemistry. And so again, without going into a lot of chemical detail, in the late 1970s, my colleagues and I at Stanford learned how to reproduce in a test tube system what up until that time, for umpteen millennia, had only occurred in the living body. And we were able to reproduce this delivery process in a test tube system. And because this was true, we could treat this as a chemical system and discover the biochemicals, the proteins that are responsible for the process, and therefore discover the underlying mechanisms for the whole range of physiology that I described is dependent on this. Now, another important element about science that sometimes non-scientists don't appreciate. The first is that you have to be prepared to make lots of mistakes in the hopes of finding the right direction, and you have to be flexible. The second is you have to find the right people to work with. You know, people have the idea that science is somebody working by themselves in isolation with a brilliant idea, etc. I'd like to think that we have occasional good ideas, but we always work with other people. And if you're lucky enough to find the right people to work with, then you're more likely to find the right way forward sooner rather than later. The first, the most important person to work with me was a young Swedish scientist in around 1980, Eric Fries. And Eric and I were actually the first to succeed to reproduce vesicle fusion and transport in the cell-free extract. Now, in order to make a cell-free extract, you have to take living cells and you have to pulverize them and disrupt them. We call that homogenization, to release their contents so you can study them in the test tube. And actually, this is the homogenizer that was actually used to first reproduce the transport process. Today, it is in the Nobel Museum in Stockholm as a gift. They asked, the Nobel Museum asked each Nobel laureate to provide a gift that commemorates their discovery, and so I was able to provide this. Now, the next step forward was taken together actually with an Italian scientist, Professor Lelia Orci, trained in Roma a physician, a brilliant man, and currently a professor of medicine and cell biology in Geneva. And Lelio and I worked very closely together to discover the process by which these trucks or vesicles form from membranes to select their cargo. And we were utterly committed to each other in a very close and warm collaboration. In fact, we named our two dogs in relation to our collaboration. Now, we were working actually on the Golgi apparatus. I've mentioned already Professor Camillo Golgi. Lelio named his dog, he is Italian, he could not let go of his heritage, he named his dog Golgi. My wife and I named our dog Buffer, because a buffer is what the biochemist calls the chemicals that are mixed with the cells, the Golgi, to make the cell-free extract. And so we produced a cell-free extract, and Lelio Orci was one, and is one, of the world's premier electron microscopists. So we could bring together the ability to visualize the intermediates in vesicle formation with the ability to study and understand their chemistry. As a result, we learned how to produce the carriers, the vesicles, in a cell-free extract. And what you see here is an electron microscope picture of many copies. Each of these is a vesicle. So what you see right here is a carrier of cargo. I want to give you an idea of size. This carrier is 500 hydrogen atoms. Hydrogen atom is a very small atom. Each of these structures is only 500 hydrogen atoms in width. That's how small it is. It's almost as small as you can imagine. And what we have done here is produce these vesicles in the test tube entirely from purified proteins. And those vesicles, as a result, we were able to isolate the vesicles and characterize their mechanism of formation. And I won't go through it in any detail, but by the early mid-1990s, Orci and I and our other colleagues learned step by step how these carriers can form on the basis of very specific protein chemical interactions. Now, the next step was to take these vesicles and observe how they deliver their cargo. Having a cell-free extract, we could isolate the vesicles made in the test tube and add them to the target membrane in the test tube. So to go back to my analogy, if you have cargo forming in Verona that needs to go to Milano, we could have a test tube full of Verona, and in that test tube produce the cargo trucks. We could isolate and separate the cargo trucks from the delivery trucks from Verona, and now add them in the test tube to Milano. We could then observe the trucks fusing or delivering the cargo to Milano. All done with purified components in a purified system. And in doing so, we were able to discover the machinery that mediates the process of delivery. And that machinery turns out to be universal. It is the same in every cell in our body. It is the same in every plant cell. It is the same in every animal cell. It is even true in yeast cells. And it's the very same machinery that mediates the release of neurotransmitters, the secretion of insulin, and mediates the division of cells and the organization of the cells into compartments. So it was a very fundamental discovery. A key individual in making that discovery is here today, actually, and now happily has a seat, my friend and colleague Felix Wieland. And this is Felix came to work with me, again, it's about people, to work with me on a sabbatical where he was a young professor at Regensburg University and an exceptionally well-trained enzymologist who had learned biochemistry from his uncle, also a Nobel laureate, Professor Lunedì, in Munich. And so Felix came and taught me how to work, and my colleagues, how to work with enzymes which are the responsible agents, enzymes and proteins. And among the many enzymes in the cell is one that we discovered together called NSF, which turns out to be the very first protein discovered that mediates membrane fusion. And for us, it was the key to opening the door to elucidating this universal apparatus that enables membrane fusion. That was in the middle to late 1980s. The next step came when another German biochemist, Thomas Solner, came to my laboratory, then in New York, and with understanding that NSF was the key, we could use this molecule to isolate the general machinery that mediates the targeting and fusion of the vesicles, which we call snare protein. And so now, after many years, and that's another, remember I said patience and urgency, we started this project in 1977. We finally discovered the mechanism in 1993. 1977, 1993, that's what? 16 years? 16 years, okay? And at that point, nobody believed us. We believed we discovered the mechanism, but my colleagues in science did not. It took another 10 years to prove that we had the right idea, okay? And the concept is actually very simple. If this is a vesicle, and this is a target membrane, the vesicle fuses with the target membrane as proteins that are called snare proteins bind to each other and zipper up between the membranes. And in so doing, they bring the delivery truck containing the cargo together with the destination to open up a hole between them that enables the cargo to be delivered. And so cells have what are called V snares in the transport vesicles and T snares in the target membranes. And the V and the T snares pair up in a very specific way. Now, the cell has many different snare proteins. It has a V snare for Milano, a V snare for Verona, and another V snare for each other city. And it has a T snare for each destination. And the V snares and the T snares assemble together, and as they assemble, they bring the delivery process, they bring the truck into the destination, and they cause the cargo to be released. Now, I don't, on this occasion, obviously want to go into any technical detail about how that works, but I hope you can get an idea that all of this complexity reduces down to some simple proteins that partner each other like a handshake, and like a just like an address that a postman has. The postman has the address, that's the V snare. The destination also has the other half of the address, and the two match each other, and the cargo gets delivered. And this magic all happens, it's not really magic, through the physical chemical process of protein folding. For those of you who are science students, I just want to illustrate this in a little detail. Imagine that this is a vesicle, and this is the V snare, and this is the T snare in the target membrane. The V snare is actually a protein, a polypeptide chain, but it is unfolded. And as you know, proteins are in a high energy state when they're not yet folded. But when they're folded, they're in their most stable, low energy state. What's very special is that the V snare here can only fold when it is bound to the T snare. So the energy that is released during the folding of the V snare is used to do work on the membranes to fuse them to deliver the cargo. The other thing that is very clever is that the V snare folds on the T snare in an organized way so as to maximize the delivery of this energy to the membranes to enable fusion. So what happens then is as the V snare is recognized by the T snare, it inserts itself into the T snare as a template and progressively folds into a series of what are called alpha helices that bring these two membranes closer and closer together as the snare pin assembles. And what is also important is that only the right V snare and the correct T snare that are shaking hands can fold together. So if your truck, which is coming from Verona to Milano, happens to encounter the T-snare of Roma, they ignore each other. But if the vesicle or the delivery truck V-snare bumps into the correct partner, T-snare, only then can they shake their hands and fold. And this continues until the membranes are under tremendous stress, tremendous pressure. They create actually a pressure in here between the two membranes. That is, we estimate, 1,000 times the pressure of the atmosphere. So these membranes are under tremendous pressure. And under this pressure, they fuse, just like that. And when they fuse, the delivery process occurs. And when the delivery process occurs, the delivery truck itself, the vesicle, is incorporated into the target membrane or the final destination. And that is why these vesicles live for such a short time. Now, finally, if any of you are having difficulty understanding what I mean by membrane fusion, all you have to do is think about a soap bubble. Because here, the V snare is one wand, the T snare is another, and the two vesicles are like two bubbles. And if you push them together hard enough, which is what the snare proteins do, the bubbles will fuse. And I think I'll skip this and just then summarize that all of these many events that I've described to you before occur as a result of these snare proteins shaking hands between membranes. And what this illustrates is that even the most complex processes in the living cell can be understood in physical chemical terms, even in very simple terms on a universal basis. So that's the sort of scientific lesson. And what it means, of course, for the future of science is that we must always continue to understand even the most basic processes in the most fundamental terms. And if we do, we create the scaffold on which we can understand the complexities of biology, the complexities of physiology, and ultimately we can understand in a rational way and develop the treatments that we need for new medicine. Now, as I've mentioned, science is a team effort. This is a picture of my laboratory at Yale. And on the morning of the announcement of the Nobel Prize, you can see that everybody is pretty happy, except for this fellow right here, and I've yet to see him smile even once, even on that day. Now, what I'd like to do is just spend the last 5 or 6 minutes drawing upon some of the history that I've just provided you of 35 years of research. As you start your endeavor, now whether your endeavor will be in research in biology as I did, or maybe it'll be in some other subject, or maybe it'll be in teaching, or maybe you'll start your own business or join an existing enterprise. I don't know. Maybe you don't even know yet. But there will be some lessons. And what I've learned, first of all, is that if you're going to do research, it takes a fair amount of confidence, just like becoming an artist takes confidence. I am oftentimes asked by students, my students, should I go into science? And what I always say is, well, don't go into science if you have any doubts. And you have to trust your judgment, because science is a bit like art. If you are working in a frontier, you don't know the answers. If you don't know the answers, you're going to be wrong. And you have to trust your intuition, because it's like looking through a fog. You know, if you're on a road and you see a glimmer ahead through a fog, through an occasional clearing of the fog, you have to interpret with some intuitive understanding what the road holds for you. And that comes from an intuitive feeling, and I think in that respect, artists and scientists are very similar. Choosing a problem, now, whether this is science, or whether you're choosing a pathway forward in business, or whatever your enterprise will be, I got some great advice from a senior scientist at Stanford, Arthur Kornberg, who was one of my heroes. And I asked Arthur, how did you choose the problem that you chose when you were young? And he said what it says here. He says, choose something that you think is very important. Keep your eye on a long-term goal. But also, choose something that you think can be done. Preferably, other people think it's very difficult and can't be done. And therefore, you have less competition. And if you get that balance right between the long-term and some intuition about what can be done, you'll be very successful. And I follow that advice. Now, another point, and this is true for science, but it's also true for anything that you do in life. If it's worthwhile, it will not be easy. Science in particular is hard. I've mentioned that you can expect failure most of the time. But I for one, always ask questions. Many of my colleagues, when I was a PhD student, were always afraid to ask. They never wanted to look stupid. Okay? I have always loved looking stupid, because it means that you're about to learn something. Don't ever be afraid to ask a more senior person about something, because if you don't understand it, the chances are other people don't understand it either. So if you will save a lot of time and effort. Troubles are good for you. And this is the first thing that probably most of you learned in your PhD thesis, is that you work on something and then it looks good and then it doesn't work. Right? It didn't always go incredibly well. There were probably some times when it didn't go well. My experience has been that when things don't go well, it's a good thing. Troubles are good for you. It means something unpredictable has happened, and you will learn from it. So I would encourage you that troubles are good for you. Now then, science is hard, another concept. I have found that people tend to go the same way over and over again. If you do an experiment or you take a path in life and it's not working out for you, try something else. You know, the hardest thing in the world is recognizing when what you're trying or what you're hoping to do is not going to work. The sooner you make a decision to do something else, whether it's in science or anything else, the better off you will be. And of course, that's the hardest thing in the world, because it involves taking your ego and reducing it. And in that direction, it's very easy to start to do something, and the hardest thing in science is to stop doing something. And I think actually this is true for just about everything. Harder to stop than it is to start. And if you can be intellectually honest with yourself, and it's very difficult to do, success will be closer rather than further away. And you'll remember I've said that science is 99% failure. A scientist who keeps on doing the first 1% is destined to fail. You have to change and change and change and be flexible. And I believe this is true in business as well. You also don't have all the answers. I've mentioned that science is a collaborative activity. Actually, success in any kind of life is a collaborative activity. Nobody has all the wisdom in the world. And whether you'll notice that I reached out many times to collaborators who taught me biochemistry. I found one of the great electron microscopists in the world, with whom we wouldn't have succeeded without that collaboration. Over and over again, I think, especially in a world that is increasingly global, where we depend on the internet as much as anything else, you should always remember to look outside of where you are, look outside of your department, outside of your family, outside of your city, outside of your country. And the more we do that, the more we will all succeed. And in relation to that, go outside your comfort zone. Now finally, having given you lots of good advice, I would just like to summarize by saying it's very good to be smart, but it's even better to be lucky. I've been very lucky. I've been very lucky in that sometimes the right people come along at the right time, even when I didn't know it. And so my thesis advisor always said, because he thought I was perhaps thinking that smart was very important, it's okay to be lucky. And so smart is good, lucky is better, and you should always be open to chance. And so this leaves me then with the overall theme that I'd like to leave you with, which is patience and urgency. And I hope that I've illustrated to you today that through my own life in science, that what I did was I took on a problem that I thought was very important, It was a long-term goal to understand a process that my predecessors had outlined for us, how a delivery process in the cell could work. It was completely unclear that it could be done. Okay, but I took a bet and a chance that maybe it could be done. And I did so with patience. But at every stage, I kept my eye on the long-term goal. I was very happy to make progress step by step by step. I tolerated failure. That takes patience. But to overcome each failure, you need to have urgency. To motivate you, to motivate your colleagues who work with you, and to continue on a pathway. And that balance is very frustrating, because if you are a patient person, we all know patient people, they oftentimes are so patient they get nothing done. We also know people who have no patience whatsoever. They're all energy, and they're doing something, but then you get nothing done. Or they do something, they do a lot, but it doesn't matter very much in the long run. If you can find the rare balance between the two, and I would say luck is important in that as much as anything else, but if you can, then you will do well, and our society, as a result, will do well. So finally, let me thank all of you for your attention, for the honor of sharing today with you. And again, I wanted to thank the many people. Altogether, there are about 300 people, young scientists that I've worked with over the last 30 years, each of whom has contributed in one or another way to this project and to my being here to talk to you today. So, thank you very much.